So today we have a very beautiful geometrical problem. We take a straight line. Now we draw two circles so that the straight line that we have just drawn is tangent to both of them. Now we draw a third circle so that it passes through the bottom contact point between the pink and the blue circle, and also it passes through both of the tangent points. Now the question over here is to find the radius of this third yellow circle if the radius of the blue circle is of 9 units and the radius of the pink circle is of 4 units. So this is Anmol, and now let us see the solution. How can we find the radius of the yellow circle? Okay, now let us start with the solution. So the first thing that you can notice over here is that I have taken the radius of the blue circle as A, the radius of the pink circle as equals to B, and the radius of the yellow circle whose radius we have to find as a variable x. Now the reason I took the radius of these three circles as variable is to generalize the solution. In simple words, we have to find an equation in which the variables a, b and x are included. And to find that particular equation, we are going to utilize the arrangement of this diagram. So the first thing we can notice is that we have the straight line and the pink circle and the blue circle is tangent to it. So let us talk about this blue circle. So the blue circle is tangent at this particular point, and also according to this arrangement, the yellow circle is also passing through that particular tangent point. So the first thing that I will do is I will draw the radius for this blue circle to this tangent point. Now we all know this particular theorem, that is, the angle at the intersection of the radius and the tangent line is always 90 degrees. Now let us do the same thing for this pink circle, as the pink circle is also tangent to the straight line and the pink circle is tangent at this particular point, and also the yellow circle is passing through that point. So now let us draw the radius, and it will be like this way, and again the angle over here would be 90 degrees. So let us remove this radius because it will create the confusion. And still remember, the radius of the blue circle has been taken as A and the radius of this pink circle has been taken as B. Now let us move on to this yellow circle whose radius we have to find. So the first thing that I will do is I will notice the arrangement of this circle. So as it was clearly given that this yellow circle, it is passing through the bottom contact points between the blue and the pink circle, and also it is passing through their tangent points. So now to utilize this particular given data, I will simply draw the radius to these 3 points in this yellow circle. So here is the first radius, here we draw the second one, and here we draw the third one. Now these 3 green line segments are simply the radius of this yellow circle, remember that. So now what I will do is I will take another color because I am going to draw 2 more line segments in this diagram, and they will play a major role for this solution. So now what I will do is I will just zoom a little bit over here. Okay, now I am going to remove this 90 degree from here because we are going to just draw some line segments over there. So look carefully at this particular point and this particular point. I am going to draw a line segment joining these 2 points, okay? And similarly on the other side, I will just remove this 90 degree first of all. And now I will draw a line segment joining this and this point. Now to move further in the solution, we have to utilize a very beautiful theorem related to the circles. If we take a circle and in this circle we take a chord as AB, so the theorem is like this way. The angle subtended by this chord at the center would be double the angle subtended by the chord at the circumference and in the same segment. So the first thing we can notice that yes, the angle subtended by this chord at the center and the circumference is in the same segment, all okay. Now according to the theorem, if the chord AB is subtending an angle theta at the circumference, this implies it is going to subtend an angle 2 times theta at the center. So this is a simple theorem related to the circles, and the proof of this theorem is also very easy. If I find a good video related to its proof, I will provide a link in the description. So now let us utilize this particular theorem in a solution. So the chord that I am going to take as the common chords are these 2 blue lines that I have just drawn. So let me just label this thing a little bit so it would be clear to explain. Now we can clearly see that the line segment AB is the chord for this yellow circle, as the point A and B, both of them lies on the circumference of the yellow circle. So we can clearly see that the angle BCA is the angle that it is subtending at the circumference. Let me just change the color so it would be better to explain, okay? So we can see that here we have the chord AB and it is subtending an angle C at the circumference, okay? So let me just take that particular angle over there as a variable and let it be equals to alpha, okay? So now we can see that the same chord BA is subtending an angle BOA at the center. So the angle BOA is present at the center and this one was present at the circumference. So now according to the theorem, the angle subtended by this chord at the center would be double the angle subtended by it at the circumference. So we have already taken the angle subtended by this chord at the circumference as alpha. Hence, the angle subtended by this chord at the center, so the center angle is BOA, that is this one, would be 2 times alpha. Okay. So now let us utilize the same theorem one more time, and this is the last time. But this time, we will take the common chord as the chord BC. Look carefully, the point B and the point C lies on the circumference of the yellow circle, hence it is the chord for the yellow circle. So we can notice that the angle BAC is the angle subtended by this chord at the circumference. The angle BAC is the angle subtended by this chord at the circumference, and the angle BOC is the angle subtended by the same chord at the center. Hence all the criteria for the theorem is approved over here. So if I take the angle subtended by this chord at the circumference, that is the angle BAC as a variable theta, then the angle subtended by the same chord at the center, that is the angle BOC, would be equals to 2 times theta. Okay, so this thing all good and nice, and now we are going to mark the final things in the diagram. So the first thing that I will do is I will draw the radius from the center of the blue circle to the point B, and the second thing I am going to do is I am going to draw one more line segment from the center of the pink circle to the point B. Okay. Now let us utilize the fact that the points A and the point C are 90 degree. So first of all, take a look at the point A. Let me just make this angle theta clear over there. So this angle over here is equals to theta. Now as we can see that this particular white line is the radius of this blue circle that has a value small a, and here we have the tangent line. Hence this complete angle was 90 degree. Now from this complete angle that is 90 degree, this much angle has a value theta. Therefore, the remaining angle that is going to be between the blue line and the radius of this circle, and it is going to have a value 90 minus theta, the greater angle minus the smaller angle. Now there is one more thing to be noted over here, and that is this line is also the radius of this blue circle from the center to the circumference, and this line is also the radius. Hence, this particular triangle over here becomes an isosceles triangle. So as we can see, these two sides are equal to each other. This implies this angle and this angle are going to be equal. One of the angle we have already got the value as 90 minus theta. Therefore, the other angle would also have a value 90 minus theta. Now, two of the angles in this particular triangle have a value 90 minus theta. Therefore, the third angle over here would have a value 180 degrees minus 2 times 90 minus theta. And at the end, this equation will give us a value 2 times theta. So we can see that the third angle over here has a value 2 times theta. Keep this thing as it is, and now let us move on to the pink circle. So in the pink circle also we are going to do something similar only. We can see that here we have the radius for this pink circle, and let me just redraw it. So here we have the radius for this pink circle, and here we have the tangent line. Hence this complete angle over there would be 90 degree. Now we can see that some part in that angle is already been taken as a value alpha. Therefore, the remaining angle that is from this radius to the yellow line. So here is the radius and here is the blue line, and the angle between them would have a value 90 minus alpha. And the radius of this pink circle we have already taken as B. Remember that. Let me just lower the thickness. Okay. So the angle between this radius and the blue line is going to have a value 90 minus alpha. And again we can see that this particular line is also the radius for this pink circle from the center to the circumference. So again we have this particular triangle over here. These two sides are ultimately the radius of the pink circle. Hence the base angles would be equal. So this angle over here would again have a value 90 minus alpha. And now using the angle sum property, the value of this angle you will get as 2 times alpha. So here we have marked each and everything that is required in this diagram. Now let us move forward in the solution by using the concept of similarity. So first of all, let us look forward to a similar pairs of triangle. So I can see one of them, and that is the triangle OBC, and this one will make a pair with the triangle RBA. So now look carefully in the triangle OBC, that is this particular triangle. In this particular triangle, the value of angle O is 2 times theta, the angle B and C are equal, each of them having a value 90 minus theta. Now look carefully in the triangle RBA that is over here. The value of angle R in this triangle is 2 times theta, and the angle B and A are equal, each of them having a value 90 minus theta. So we can see that in both of these triangles all the three angles are equal, and we have just labeled them according to this correspondence. Correspondence means the first angle should be equal to first angle, the second one with the second one, the third one with the third one. And the reason we write according to this correspondence is because the next step that we are going to do is we are going to take the ratio of their sides equal, and that is what the similarity says. Once two triangles are similar, the ratio of their sides become equal. So let us take the ratio over here as equal. So OB upon RB, this ratio would be equals to OC upon RA, and this one would be equals to BC upon BA. Now we can see that some of these line segments are already the radius of this yellow and the blue circles, hence they would have a value as variables A and X respectively. Like for example, the length OB is the radius of this yellow circle, hence it would have a value X upon RB, that is going to be the radius of the blue circle that is over here, hence it would have a value A. This thing equals to OC. OC is again the radius of this yellow circle, hence it would have a value X upon RA, that is the radius of the blue circle, hence it would have a value A, and this thing equals to BC upon BA. Now look carefully in this diagram. The length BC and the BA are the yellow color line segments that are ultimately the chord for the yellow circle. So there is no particular length given to them, so let it be just BC upon BA only. So now we have this particular equation, and we can see that these two terms are already equal. So now what I'm going to do is I'm just going to take this much part from this equation because that makes sense. So we have the equation as BC upon BA, the ratio of these two chords equals to X upon A, and I will take this as equation number 1. Now let us take the second pair of similar triangles in this diagram, and I think you might have already guessed. So the first triangle is the triangle OBA, and this is similar to the triangle QBC. So we can see that in the triangle OBA and the triangle QBC, all the three angles are equal, and this makes these two triangles similar to each other by the property of angle, 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 and I have already written the names according to this correspondence. Now let us equate the ratio of their side. Therefore, OB upon QB. So OB is the radius of the yellow circle having a value X upon QB, that is the radius of the pink circle having a value B, equals to BA upon BC as it is, and this thing equals to OA upon QC. So OA is the radius of this yellow circle having a value X upon QC, that is the radius of the pink circle, hence it would have a value B. So here we can see that we have an equation of the ratios, and from this I will again take these two things equals to each other. So now we have BA upon BC equals to X upon B. I will just reciprocal both of the sides in this equation, hence I will get BC upon BA equals to B upon X, and let this thing be equation number 2. So now recall the first equation, and just now we have got the second equation. One common thing between these two equations is that the left hand side of both of the equations are similar, that is BC upon BA. Hence we can compare the right hand side of both of this equation, and that will give us the result as, so the right hand side of the first equation, that is X upon A, equals to the right hand side of the second equation, that is B upon X. And now by doing the cross multiplication we will get X square equals to A into B, and by taking the square root on both of the sides I will get the value of X equals to square root of AB. And recall that X is the radius of the yellow circle, A is the radius of the blue circle, and B is the radius of the pink circle. And here we have got a very beautiful relation between them, that is the radius of the yellow circle is equals to square root of the product of the radius of the pink and the blue circle. Now let us find the answer to this particular question that was asked. So in the question it was given the radius of the blue circle is having a value 9, the radius of the pink circle is having a value 4, and the radius of the yellow circle we have to find. So now as we have the relation, therefore the radius of the yellow circle would be equals to square root of product of the radius of the blue and the pink circle. Therefore square root of 9 times 4, that is going to be square root of 36, and square root of 36 has a very nice value, that is 6. Therefore, the radius of the yellow circle is equals to 6 units, and this is the answer that we were looking for. So this was my way to solve this particular problem. If you have any other method other than this, do comment below. And if it's hard to comment, or else if you have to share any kind of picture for the solution or for a problem, you can email me, or else you can send it to me on my Instagram. The link is in the description.